Good. So welcome to the next lecture of selected topics in graph theory. During the last two lectures, we were giving an introduction into the spectral graph theory, and in particular, we looked at the spectral gaps of graphs, or rather of adjacency matrices of those graphs, and the relation to combinatorial properties of the graph in question, more precisely vertex and edge expansion. So one thing that we did not do so far, and what we will do during this lecture, is to actually show that there are graphs with good expansion properties. So-called expanders. So this lecture will be about making a deterministic construction of large expander graphs of constant degree. And there are different constructions of expanders in the literature. The one that we are going to present during this lecture is probably the combinatorial, the simplest, and also the most useful. It is called the zigzag construction, or the construction through the zigzag product that we will define later on. There are some earlier constructions using number of theoretical tools, but we will not delve too much into them at this point. So recall that what we are going to construct are so-called expander graphs, and a graph is an ND alpha expander, where alpha is a constant from, say, 0, 1. If the following holds. First of all, the first component denotes the number of vertices of my graph. So an ND alpha expander is a graph on n vertices, and it is deregular. So the second component is the regularity. And the last component is the thing that we are mostly interested in. This is the spectral. This denotes the spectral properties of the graph. So if I denote by lambda of a graph G, the second largest up to absolute value eigenvalue of the graph, so the maximum of the absolute value of lambda 2, the second eigenvalue, and lambda n, the last eigenvalue. Then this alpha is the smallest integer, such that this number, this maximum, is smaller or equal than alpha times d. So in other words, if I have an ND alpha expander, then its spectrum looks like that. There is one eigenvalue d, which is always there due to deregularity, and all the other eigenvalues are there here in this interval between minus alpha d and plus alpha d. So if, for example, alpha is equal to, I don't know, 0.5, then all the eigenvalues apart from this one largest one need to be sort of concentrated around 0. And this gap between the largest eigenvalue and this interval containing all the other eigenvalues, this is called the spectral gap. So we are interested in constructing expanders, ND alpha expanders, where alpha is significantly smaller than 1. Yes, because this will give us good properties, spectral properties of the graph, which will translate to good combinatorial properties, such as rapid mixing of the Markov chain, of the random walk on the expander, or good edge and vertex expansion. Good. So the theorem that is true, that can be proved, is that there is some constant d. Yeah, so say d1000, and there is some alpha from 0, 1, such that you can always find for every n, you can always find an ND alpha expander. Yeah, so a graph with good expansion, and moreover, such an expander can be constructed in polynomial time, and importantly, in deterministic time. Because as I said earlier, it is quite easy to actually prove that there exist expanders by just sampling a deregular graph, and proving that it has good expansion properties. We have not done it yet because this is a bit technical, but maybe we will do it during the tutorials. However, the important part about this theorem is that actually such ND alpha expanders can be constructed deterministically. So this is what we will not prove, because like getting this exact statement requires some technical work, which is not that interesting. We will prove a little bit weaker statement, and we can start looking like the following. So there exists a constant d, Yes, so say 1000, it will actually be a bit larger, such that for every integer t, I can find an expander that is d square regular, that has alpha equal to 2/5. So it will be significantly smaller than 1. And the number of vertices n is equal to d power 8t. And moreover, such expanders can be constructed in polynomial time and more precisely in deterministic time. So how these two statements differ? So in here, I said that I can find an expander for every possible n. So for n equal to 1, 2, 3, 4, 5, and so on and so on. In this statement, I'm requiring that the number of vertices is a power of d. Yeah, actually a power of d to the 8. So in particular, we'll not construct expanders for every possible number of vertices, but we'll just show a growing and growing family of expanders. Yes, with the sizes of the vertexes growing exponentially. And this will be good enough for most of the applications that we will see next week. How do you actually get from this theorem B that we will prove the theorem A that is true? Is that what you do? You construct expanders like that with the number of vertices being a power of d to the 8. You take the smallest possible expander such that you have at least n vertices, and then you simply do some patching in it. You simply throw away some vertices and patch the graph to a regular graph usually by adding some loops to the vertices. And you need to be careful when you are doing this, because you need to make sure that the spectral properties are still preserved, meaning from this alpha equal to 2/5, you do not get too large eigenvalues, but this can be done, and this is a bit technical. So we will skip this implication because it is less interesting and focus on the proof of theorem B. So deterministic constructions of large and large expanders. Good. Are there any questions at this point about what this theorem statement says and what we are going to do? Okay, if not, then I hope that this is clear, because so far nothing happened. But let me now go a little bit more into the details, and let me say what will be the strategy for the proof. Yeah, what will be the idea for how we are going to construct those expanders. So first of all, we will start from some reasonably good constant size expander, say G1. Yeah, so we'll first explicitly construct a small expander. For this, we will use some number of theoretic construction. We will actually do it during the tutorials. So we start with some G1, and then starting from this G1, we will actually construct larger and larger expanders using kind of an iterative process. So from G1, it will be not exactly like that, but imagine for now that from G1 we will construct G2, from G2 you will construct G3, then G4, and so on and so on. And every time I'm constructing the next graph, I am multiplying the number of vertices by d to the 8, while keeping the regularity fixed. Yep. And keeping also the spectral properties fixed. So in this way, the consecutive graph G1, G2, G3, and so on will create this family GT that was promised in the theorem. Yeah? So during this process, we will need to, the crucial part will be about controlling the spectral properties of those graphs. So we'll need to control the spectral gap of in each of those graph GT, and during this construction, and therefore we'll mostly focus about on algebraic operations so we will construct the consecutive graphs using various algebraic operations that will enable us to somehow understand how the spectral properties of the next graph depend on the spectral properties of the previous. Good. So now before we go to that construction, I will we'll review the operations that we will use. Yeah. So one operation we have already seen during the previous lecture, and this is the operation of squaring a graph. Yeah, so from graph G, I can get a graph G squared. Yeah. So the graph G square is a graph on the same vertex set as the original graph. Yeah. And how do we define edges in G square? For every so essentially we are defining them using two walks in the original graph. So for instance, if I have some graph G, say a square, and I would like to now square this square, and I would like to understand how many edges I put between a vertex U and a vertex W, then I count how many walks of length 2 I have in the original graph from U to W. So for instance, for here from U to W, I have two walks of length 2. I can go through this vertex, or I couldn't go through this vertex. Yeah. So in the square of this graph, I get two edges between U and W. Yeah. Then similarly, between this vertex and this vertex, I also have two edges. But note that, for example, on one side of this square, yes, from this vertex here, U, to this vertex V, I do not have any edge in the square of this graph because I do not have any walk of length exactly to between these two vertices. Yeah, but I also allow walks going there and back. So for instance, from U, I can go back to U on two possible ways, either going through V or going through V prime. So I put two loops at vertex U, and similar for all the other vertices. Yeah. So in other words, every walk of length 2 in G contributes to exactly one edge in G square. So if I have a graph G here that is a C4, then this is a graph G square. Good. So what are the properties of this construction? First of all, it's easy to see that the square of a graph is, if I have a graph that is D regular, then the square is D square regular. Because if I start at any vertex U, how many walks of length 2 I can implement from it? I can first I have D choices to choose the first edge to go through, and then another D choices independently for the second edge. Yeah, so the graph is now D square regular. Yeah, and here this was 2 regular, and this is 4 regular, as it should be. Yeah. So now the main idea behind this construction is that we really understand how the adjacency matrix of the square of a graph looks like, because it's just the square of the original adjacency matrix. Yeah? Because doing 2 steps of a walk in G corresponds in the algebraic terms to squaring the adjacency matrix. This we have seen already during the previous lecture. So in particular, if I look at the spectrum of the graph G square, so the eigenvalues of the adjacency matrix of G square, because the adjacency matrix is just the square of the original adjacency matrix, then in the diagonal form, yes, this matrix is being just squared. So just every eigenvalue on the diagonal gets squared. So if the spectrum of G consists of lambda 1 up to lambda n, then the spectrum of G square consists just of squares of this original eigenvalues. Yeah. So we really understand how the spectrum of the square looks like. So in particular, if I look at the alpha of G square, where alpha is this ratio between the largest non-trivial eigenvalue up to absolute value divided by the regularity in G square, the regularity is D square, right? And what is the largest up to absolute value eigenvalue of G square? Well, if the eigenvalues are simply squared, then this is bounded by alpha of G times D. Yeah, because this was the largest eigenvalue up to absolute value of the graph G. Yeah, so now D square cancels out, and I've got alpha of G square. So for instance, if I have an ND, say 1/5 expander, G is an ND 1/5 expander, then G square is an N D square and 1/25 expander. Yeah. So the number of vertices stays the same. The regularity goes up. Yes. And the spectral gap becomes better because it becomes squared. Yeah. So this is an operation that enables us to get a better spectral gap. Yeah. by squaring the graph at the cost of increasing the degree. Yeah, the number of vertices stays the same. Yeah, so the degree of the graph increases while the spectral gets better. So we can trade one for the other. Are there any questions to this operation? And if not, then please put the +1 in the chat so that I see that that there are no problems. Okay, I see a number of +1s, so let's just continue. So this is one operation that we'll use. Another operation is the operation that we have seen during the tutorials last week, which is the tensor product of two graphs. Yeah? So the tensor product of two graphs, G and H, yes, is a graph whose vertex set is the product of the vertex set. So you can think about the vertices of the product as pairs of vertices of the original graph. Yeah. So for instance, if I have here a path, yes, and I make a tensor product of it with a path, then the vertex set will be essentially a grid. Yeah. So for every row and column, I will here have a vertex. Yeah. And whenever I've got an edge UV in one of the graphs and I have an edge AB in the second of the graphs, I put the following edges in the product. So between vertex UA, I put an edge to the vertex VB. Yeah. So I put an edge between any pair of vertices UA and VB whenever I can travel in the first graph on the first coordinate and in the second graph on the second coordinate. Yeah, so by just reversing the edge UV to the edge VU, which is there as well, I also get an edge like this between UB and V. Sorry, this should be actually VA. Yeah, so between UB and VA. Yeah. So you can easily memorize this how this product works by seeing this cross, that whenever you're doing an edge times an edge, then you get across those cross edges here. So for instance, to see an example, if I take a path times a path, so say a P4 times a P4, then what do I get? I simply get those crosses all over the place in those cells of the grid. Yeah, because each of those edges times each of those edges creates this cross between the four corresponding vertices, right? So this is the tensor product of a path with a path. So what are the spectral properties of this construction? First of all, what about the regularity? So if G is, say, DG regular and H is DH regular, then you can easily see that that the product is DG times DH regular. Yeah. Why so? Because, well, whenever I have a vertex UV in the product, sorry, UA in the product, how many different vertices I am adjacent to? Well, I can change the first coordinate on DG options. I have DG options how to change the first coordinate, and have DH options how to change the second coordinate. So you have DG times DH neighbors in total. Yeah. So one thing that we will not prove here during the lecture, but we have already sort of seen it during the last tutorial, and we will see it more explicit during this tutorial, is how the spectrum behaves during the tensor product. Yeah. So the idea is that the spectrum is being pairwise multiplied. So if the spectrum of G is, say, lambda1 up to lambda, the number of vertices of G, and spectrum of H is mu1 up to mu, the number of vertices of H, then the spectrum of G times H is essentially the spectrum of G times the spectrum of H, in the following sense, that I simply take any eigenvalue from here, any eigenvalue from there, and I take the product. Yeah, so you pairwise multiply the eigenvalues. And it is quite easy to see this, because if I have a vector, say, xi corresponding to the vector, to the eigenvalue lambda I, and you have say yj is the vector that is eigenvector that corresponds to the eigenvalue mu j. Then the eigenvector corresponding to lambda I mu j is the eigenvector xi tensor yj. Yes, and this vector is defined as what do you put at say uv, at what do you put in this vector at the coordinate corresponding to a vector u comma v. You put what you put in xi corresponding to u, and on the coordinate corresponding to u, and you put what you put in yj at the coordinate corresponding to v. Yeah, so you essentially make a pairwise multiplication of the eigenvectors, and you get eigenvectors of the product corresponding to the product of eigenvalues. Good. So this is how the spectrum behaves during a tensor product. And what does it mean for the spectral gap? So what is alpha of g times h? So again, this is the maximum non-trivial eigenvalue divided by the maximum eigenvalue, which is the regularity. So the regularity is dg times dh. And what will be the maximum eigenvalue, non-trivial eigenvalue? Well, if I try to look at the second largest eigenvalue of this product, and I know that the spectrum is the pairwise product, and the second largest will be either I take the first largest from one graph and multiply it by the second largest from the other, or vice versa. Yeah. So the second largest eigenvalue of g times h is the maximum of the following two quantities: the second largest eigenvalue up to absolute value of g times the irregularity of h, yeah, or the second largest eigenvalue of h times the regularity of g. Yeah. So now, if you put the regularity under the brackets, this is the maximum of lambda divided by dg and mu divided by dh. Recall that lambda is the maximum of the absolute value of lambda 2 and lambda n. Yes, and the same for mu. And this animal is simply alpha of g, and this animal is simply lambda alpha of h. Yeah, this corresponding ratio. Yeah, so the spectral parameter alpha of the tensor product is simply the worst of the two spectral parameters I started with. Yeah, so in other words, if I take a tensor product of two graphs that are good expanders, I get a graph that is a good expander. This is the moral of the outcome of this construction. So to summarize, what this tensor product construction achieves. Yeah. So the number of vertices grows. Yeah, because now we have the new vertex has the vertex that is the product of the two vertex sets. So we get more vertices in this way. The regularity also increases, so the degree of the vertices increases, and the spectral gap stays more or less the same in a sense. So if we had two graphs that were already good, we will not get worse spectral properties by making tensor product. Yeah. So if you look at these two operations, squaring and taking a tensor product, you see that both of them have this property, that the degree increases. Yeah. So we can actually get larger and larger graphs. Yes. And graphs with better and better spectral properties, but always at the cost of increasing the degree. We do not have at this point any operation that decreases the degree of the graph. And this operation that we now need, yeah, will be exactly the zigzag product that we'll define in a moment. So this is the key operation that is enabling us to make this whole approach work. This will be a way to decrease the degree of an expander at the cost of slightly worsening the spectral properties. Good. But before we go to the zigzag product, are there any questions about the tensor product? Otherwise, put a +1. Okay, I see a number of +1, so I hope that this is so far understandable. So let's go further to talking about zigzag product. So the zigzag product, so far I will not define. The definition will be a little bit more complicated. We'll do it later. But first, I would like to speak about the properties of the zigzag product. So first of all, what kind of graphs I can multiply using the zigzag product? So I need the following: graph G, the left-hand side graph in the zigzag product, needs to be say ND alpha expander, where D is the capital D. So this is a graph that has n vertices and has regularity capital D. And now for the right-hand side in the zigzag product, for the right graph in the zigzag product, I need to have a graph H, which say is D regular for some small d, yeah, but its regularity needs to its number of vertices needs to match the regularity of the left graph. So essentially, you can think about it as follows: that what will happen, this is not exactly what will happen, but roughly what will happen is that we will take graph G, here will be graph G, and then we will replace every vertex of G by a copy of the graph H. And then if graph G had a vertex with say degree 3, then we will need to have the property that the graph H has exactly 3 vertices, so that the 3 edges outgoing from this vertex before taking the product will be redirected to the 3 different vertices of H. Yeah. So essentially what will happen is that every vertex of G will be replaced by a copy of H, and the edges will be redirected to different vertices. Yeah. So therefore the regularity of the host graph of graph G needs to be equal to the number of vertices of the graph that we substitute with. Yeah. So if we have such two graphs, we will be able to define the zigzag product of them. So this is usually denoted G zigzag H. Unfortunately, in tech there is no way of writing this. You need to use some other hacks to do it. And this graph will be a graph with the following properties. So first of all, the vertex set will be the product of the vertex sets. Yes, and you can already see this in this picture. Essentially, every vertex of the product will be defined by saying in which original graph of G I am and which of the vertices of H I am a copy of. Yes, so this the zigzag product will use the product or the Cartesian product of the vertex set as the vertex set, and the zigzag product will be actually D square regular. Yes, so we'll not exactly get the regularity of H, but we'll get the square of the regularity of H. So this will just come out of the construction. And the main idea of the zigzag product is that taking a zigzag product does not deteriorate the spectral properties too much. So if G is an N capital D alpha expander, and H is an say D beta expander, yes, then then alpha of the zigzag product, so the ratio between the highest non-trivial eigenvalue and the regularity, is bounded by alpha plus beta square. So you should read it as follows: this alpha is the alpha of G, yes, is the spectral parameter of the graph G that is the host graph. And then if I replace every vertex with this copy of H in the zigzag product, the spectral parameter alpha can deteriorate a little bit, but if H is a good expander, it will only increase a bit. Yeah. But the main goal of this construction is that if we go from G to G zigzag H, then from a D regular graph where D can be very large, we get a graph that is only d square regular. Yeah. So in other words, the zigzag product, the thing that it achieves is that the degree strictly decreases if d is much larger, capital D is much larger than d square, while the spectral gap gets worse only a bit. Yeah. And the side effect, the number of vertices increases a bit. Yeah, by multiplying by h. Yeah. So these are the three properties that we have, and you see that these are properties are sort of in contraposition to the properties of, say, squaring. Yeah, where the degree was increasing while the spectral gap was getting better. Yeah. So now we have the two operations, zigzag and squaring, and they sort of are in contraposition to each other. Yeah, one gets a better degree while sacrificing on a spectral gap. The other gets get better spectral gap while sacrificing the degree. So the idea of the construction, the inductive construction, is that we will alternate those two operations, squaring and taking a zigzag product, in order to get larger and larger graphs, mostly due to this fact that in the zigzag product the number of vertices increases. Yes, while the spectral gap will be controlled by squaring, will be dumped down by squaring, while the degree will be controlled using zigzag products. Yeah. So we will also use the tensor product during the construction, but this will be mostly for technical reasons. Good. Are there any questions about zigzag? So I did not define the zigzag so far, but I stated its properties. Good. If there are no questions about the zigzag, let me before I give you the definition of the zigzag and the proof of this lemma about the spectral behavior, I will now prove the theorem based on the stated properties of the zigzag. Yeah. So now we give this inductive construction of the graphs G1, G2, G3, and so on, based on the assumed properties of the zigzag product. Yeah. So in this construction, we'll need some base expander H. Yes, this will not be actually not equal to G1, but it will be a graph that will be always somewhere there during the construction. And this is, we will assume that this is an expander that is a d to the 8, comma d, comma 1/5 expander. Yes, so the number of vertices is d to the 8, the regularity is d, and alpha, the spectral parameter, is 1/5. Yes, and for this we will make a direct number theoretic construction of such an expander. It's actually pretty cute, and we will do it during the tutorials. Yeah. So for now, suppose that that we have such an expander in our hand for some constant d. Yeah. Actually, in the whole construction, this d will be equal to, say, 1000. And you will be able to hard code this expander in the construction. Yeah. So now we define the consecutive graphs G1, G2, G3, and so on using the following recursive formula. So first of all, for G1 and G2, I define G1 to be h squared. Yeah, so I square the base graph. And for G2, I take the tensor product of h with itself. Yeah. So you can easily see that this means that the number of vertices of G1 is what? D to the 8, well, because the number of vertices of H was D to the 8, and the number of vertices of G2, because this is the product of the number of vertices of H with itself, this is D to the 16, so as it should be. And also you see that G1 is D square regular, and G2 is also D square regular. Yeah, because recall that we are aiming at each GT being D square regular. Yeah. So then for the next items in the next entries of the sequence of our expanders, we take the following magical formula. I take two graphs that I have already defined before, roughly like GT half and GT half. Once I take a floor, once I take a seal in order to get here really integers. Yes, I take their tensor product. Yeah, I then square this graph. Yes, and then I zigzag it with my base graph. So this is the construction. Yeah. So this tensor product is essentially not really necessary. It will be useful and for what I will say in a moment. But these two operations are crucial. Yes, squaring and zigzagging. Because what will happen is that squaring will increase the degree while also getting better spectral properties. Yes, will making alpha smaller, and then zigzagging with h will again decrease the degree to a constant while worsening the spectral parameter a bit. Yeah, so by alternating these two operations, we keep both of the parameters in check, both the regularity and alpha. Yeah. So as I said, this in this description, this tensor product isn't really necessary. I think that everything would go through without problems if I just take the previous graph, I took it to the power 4, like square and then square again, and then I took a zigzag product with h. So the whole construction, I think it would go through without problems. But we will actually need this particular formula, this particular form during the next lecture. Yeah, because what we will need during the next lecture, as far as I remember, is that it's not that you define GT based on GT minus 1, then GT minus 1 based on GT minus 2, and so on, but you construct those extenders essentially using iterative squaring. So at the end, you define GT based on GT half, then on GT over 4, and so on. So you have a logarithmic depth of this construction instead of linear depth in T. And during the next lecture, what we will do, we will use the expander constructions to give some algorithm working in logarithmic space. And the fact that we are able to emulate all these constructions in logarithmic space will be essential for the application. Good. So let's now check that this construction has all the properties. This construction is first of all well defined, and then it has the property that we want. Yes, that the graph GT has exactly d to the power 8t vertices, that it is d square regular, and most importantly, that alpha of GT is bound by 2 over 5. So this is so all these conditions combined will prove to us that GT is an d to the 8t comma d square comma 2 over 5 expander, which is what was promised in the theorem statement. Okay, so not surprisingly, we'll do this by induction. And the base case we essentially already did. So the first graph G1 has d to the 8 vertices, G2 has d to the 16 vertices, this we checked, and both of them are d square regular. Yes, so it remains to ask oneself what are the spectral gaps of this spectral parameters of these two graphs. So alpha of G1, well, this is alpha of G1. Recall that G1 is h square. H was a 1 over 5 expander. Yeah, so this will be bounded by 1 over 25. Yeah, so I've got this here. On the other hand, recall that G2 was defined as H tensor H, and tensor product of two graphs with alpha being 1 over 5 will also have alpha bounded by 1 over 5, so this is bound by 1 over 5. Yeah. So these two properties are good. They are actually much better than what we expect. Yeah, we expect only 2 over 5 for the parameter. So now we come to the crucial point, which is the induction step. Yes. So now we need to prove that, assuming that the previous graph already have those properties, defined here. The next graph defined using this this magic formula will have the same property. So first of all, what is the number of vertices? Yeah, so this graph here has by induction d to the power 8 this seal vertices. This graph has this many vertices, and then taking a zigzag product with h will multiply the number of vertices by the vertex size of by the size of the vertex set of h, which is d to the 8. Yeah, so now the seal and the floor of t minus 1 half, they add up to t minus 1. So you've got here d to the power 8 t minus 1 multiplied by d to the 8, and you've got d to the power 8 t as expected. Yeah, so this was the proof of the vertex that has the right size. Good. So what is the regularity of this graph GT? So by induction, these two graphs that were defined before, they are both d-square regular. Yeah. So this means that this graph, their tensor product will be d to the 4 regular. Yeah. And then if you square a d to the 4 regular graph, you get a graph that is d to the 8 regular. Yeah. So this graph, the right-hand side, the left-hand side of the zigzag product is d to the 8 regular. And this is perfect because recall that h has d to the 8 vertices. Yes, which exactly matches the regularity of the host graph. Yeah, so this means that that this zigzag product is indeed well defined. Yes, this I also need to check. And then by the properties of the zigzag product, the result of the zigzag product is d-square regular if the right hand side graph in the zigzag product was d regular. Yeah. So then we have the induction step working. Yeah. And finally, and most importantly, we need to check the spectral property and the spectral parameter alpha of this graph in question, GT. So by induction, we know that both those graphs that we start with, G seal of t minus 1 half and GT floor t minus 1 half, they have alpha bounded by 2 over 5. So this means that when I take the tensor product of them, still alpha is bounded by 2 over 5. Yes, this is the property of the tensor product. Then when I square it, the alpha gets squared as well. So the alpha will be bounded by 4 over 25. And then recall that alpha of GT, yes, this is the zigzag product of this animal with H. And then this is bounded by the alpha of this plus alpha of this plus alpha of this square, which is 4 over 25 that we have here. And H was an d to the 8 d 1 over 5 expander. Yes. So then this 1 over 5 comes here, and here I've got this 1 over 5 squared. So I've got 4 over 25 plus 1 over 5 plus over 1 over 25, and magic 2 over 5 again, and the induction goes through. Good. Good. So we proved by induction all these properties, assuming that we have this magic zigzag product construction that we have not defined so far. Are there any questions to this proof? And if this is clear so far, please put a +1. Okay, I see that the number of +1 slowly start to be smaller. Could I clarify anything for those of you who got lost? Okay, if there are no questions, maybe we'll just continue further, because this is sort of a bottom line of this expander construction, and now we need to fill the major gap in this construction, which is the definition of the zigzag and proof of the property of the promised property of the zigzag. So imagine I've got two graphs that I would like to zigzag. So G is a d-regular graph for some capital D, and H is a graph with D vertices. Yeah. So on this example, G is a 4 regular graph, and then H has exactly 4 vertices. It is a 4 cycle. Let's call those vertices somehow maybe A, B, C, D. Yeah. So the first thing you do in Zigzag, this is not yet the Zigzag product. It is something called the replacement product, and this is exactly what I told you about before. So you now take every vertex of G, yes, and you replace it with a copy of H. Yeah. So you put a copy of H and you redirect the edges of G to different vertices of H. Yeah. So you need to be a little bit careful in here, and this might not be the best example that I chose here, because this H is it's a vertex transitive graph, so it essentially looks the same from every point of view. But when you are putting a not really that symmetric graph into G, you need to. There are different possible ways of how to put H how to substitute a vertex of G with a copy of H, right? So whenever you are doing the substitution, you should somehow index the edges outgoing from a vertex with the vertices of H. And then when you are doing the substitution, you redirect the A edge to the vertex A, you redirect the B edge to the vertex B, you redirect the C edge to the vertex C, and so on and so on. Yeah, so sort of the replacement product and the zigzag product as well is kind of parameterized by how at every vertex you label the incident edges with the vertices of H. Yes, and this is the template for rewiring these things. Yes, and the same for the other vertices. So for instance, here I could also label the outgoing edges with the vertices of H, A, B, C, D, and then this would correspond to here putting A, here putting B, here putting C, here putting D. So in particular, observe that vertex B from this copy is being connected with vertex D from that copy. Yes, so these two labels might not match, meaning that this edge might have a different label from the point of view of one endpoint than from the point of view of the other, and so on. So this is called the replacement product of two graphs. This is not yet a zigzag product, but almost. So now we make it a zigzag product. And in the zigzag product, we will put one edge for between, say, a vertex UA and VB, where this is a vertex from G and this is a vertex from H. Yes? Whenever I will have a walk of length 3 of the following kind. So for instance, on this picture, there would be an edge between this vertex and that vertex. So the walk of length 3 must first walk along an edge of H within one of those, I will call them clouds. Yes. Then take the unique edge of G going out of this vertex, and then choose one of the edges within this cloud and finish here. Yes. So for instance, for this walk of length 3, yes, I would put one edge in the zigzag product. Or for instance, from this vertex, maybe I'll choose another color. For instance, from this vertex in the zigzag product, I have an edge to this vertex because I can go along the CD edge in this cloud, then jump between the clouds in the only possible way, and then proceed to this vertex here. Good. Is the definition of the zigzag product clear?
I have one. Do we keep the old edges in the zigzag?
No. Well, there are no old edges in a sense, right? You mean the edges from the replacement product?
Yeah.
No,
those.
we don't keep them. We don't keep them. Similar as in the square of the graph. Yes, we don't keep the original edges. In here, we simply the edges of G zigzag H in one-to-one way correspond to those kind of walks of length 3 in the replacement product. Any more questions? Or otherwise put a +1 if you understood the construction. Okay, I see some +1, so I hope that it's kind of understandable what is going on here. So now observed, what can we say about the regularity of this graph? So how many other vertices I can reach in the zigzag product from any vertex of G zigzag H. Yeah. So how many ways I can choose such a walk of length 3? Well, there are only d square ways to choose it. Because first I have the possibilities of choosing an edge within the cloud, because the graph H, the ground graph H is irregular. Then I have a unique choice of how I travel along an edge originating from G. And then I have another d choices of choosing an edge within the next cloud. Yes. So this means that from every vertex of the product, I have d square ways of creating a walk like that. Yes. And this means that the product will be d square regular. Yeah. So we see that indeed the regularity is much better than the regularity of G. Yeah. So now, at least, what is my intuition behind this construction? So essentially, if you are doing a random walk in the graph G, whenever you are standing at a vertex, you need to choose the next edge. And there are capital D choices for the next edge. Yeah, which can be large, meaning we would like this to limit this capital, this degree capital D to something smaller, while still preserving that the graph is sort of a good expander, which corresponds to the random walk being rapidly mixing. So now, instead of choosing log capital D random bits in order to choose the next neighbor, you're replacing this choice with a pseudo random choice based on the graph H. So instead of choosing one in D options, uniform at random, you are doing a one step of a random walk in H, which is sort of a pseudo random process. We have seen that walking on an expander is rapidly mixing. It quickly converges to a uniform distribution. However, now instead of making a one in D choice, you are actually making a one in small d choice. Yeah. So essentially, this intuition shows is that if you replace every vertex with this copy of H, and if H is a good expander already, yes, then the spectral properties of the graph G should not deteriorate too much during making this expander, this zigzag product. So this is my intuition behind why this operation makes sense, and in particular why this operation preserves sort of preserves the graph being a good expander. Good, but
sorry,
now
could you repeat why this is d square regular? Because like if we choose two edges in H, we don't have guarantee that they are connected in G, or do we have?
I do not understand.
Okay, because there is
let me repeat, because I guess this was this might have been confusing. I stand in a vertex of G zigzag H. How many ways I have of making a walk of length 3 looking like that? Yeah, first an edge of H, then an edge originating from G, and then an edge of H. I need to first have D choices for choosing the edge in H. Then I have a unique choice of the edge originating from G that comes from this vertex. And then I have, again, D choices for choosing the last edge of H. Yeah. So in all, I have here D choices. Here I've got only one choice, and here I've got D choices again. Is it clear now?
Yes, thank you.
Yeah. Okay, good. Good. So to repeat, the intuition is that by replacing the one in capital D choice in the random walk on G with a pseudo random choice based on a random walk in H, one step of random walk on H, this operation should not deteriorate the spectral properties of the graph in question. At least this is my intuition. But more formally, what we need to prove is that if G is an ND alpha expander, yeah, so it has this ratio between the second largest and largest eigenvalue being bounded by alpha, and H is an D, capital D, small d, beta expander, then G zigzag H is an ND, D square alpha plus beta squared expander. Yeah, so these two properties are clear, yeah, because the number of vertices is just multiplies. We have already seen that this is a D square regular graph. So what we need to prove is this thing, yes, that the alpha of G zigzag H, yes, is bounded by alpha plus beta square, yes, where alpha and beta are the spectral parameters of G and H respectively. Yeah. Okay, so as usual in all those proofs, yes, we need to ask ourselves how to understand the zigzag product in terms of algebra. Yes, how to express the adjacency matrix of G zigzag H. So let B be the adjacency matrix of G and C be the adjacency matrix of H. So this is a square symmetric matrix of dimension n times n. Yes, and C is a square matrix of dimension D, capital D times capital D, right? So then the adjacency matrix of G zigzag H will be a matrix ND times ND, right? And we need to understand how it looks. And you can understand it like that. So if you are doing a one step of a walk in A, then this corresponds to three steps of walks, one in the graph H, one in the graph G, and one in the graph H again. Yeah, but not quite, because instead of having one graph H, for instance, when walking in H, we have actually n copies of the graph H corresponding to the different vertices of G. Yeah. So I can understand the adjacency matrix of A as the product of the matrices. I will call them C hat, B hat, and C hat again, where C hat is the matrix of walking within the clouds. Yes. So you have now the n copies of the graph H. Yes. And there you have some edges inside those copies. Yes. And if you want to have the matrix of this graph consisting of n independent copies of the graph H, then this matrix is simply like a block matrix where you have here n blocks equal to the adjacency matrix of H put on the diagonal. Yeah. So then, taking one step in the respective copy of H corresponds to multiplying by this matrix C hat. Yeah. So now B hat is a little bit more difficult to imagine. Yeah, because essentially B hat should look like the matrix B. However, this was an n times n matrix, and this is now an ND times ND matrix, where essentially the edges are now being dissolved into like every vertex is being dissolved into different vertices, and the edges are being rewired accordingly. Yeah, so in particular in the matrix form, this means that every entry of the matrix B is being replaced by a block of dimension D times D in the matrix B hat. Yeah, so for instance, if I have a 1 in the matrix B, then this one is being replaced with a block of dimension D times D, where I put all zeros, yes, apart from 1, 1, which exactly corresponds to the vertex from one cloud versus the vertex from the other cloud, how they are wired together. Yeah. So so this is how B hat is being obtained from the matrix B. Yeah. So in particular, observe that B hat is a matrix of a graph that is essentially matching. Yeah, because this is a matching between these different endpoints. This is how the graph that B hat represents looks like. Yeah, so this is a matching consisting of those detached edges originating from G. So in particular, this B hat is a matrix of a matching And the matrix of a matching is a symmetric matrix, as usual for graphs, but it is a permutation matrix. Yeah, so every row and every column has exactly 1, 1, corresponding to where do I go to the vertex that is matched to me. Good. So now we have these two properties. C hat is a block matrix of this form. B hat is being obtained from B by this kind of a replacement, and it is a symmetric permutation matrix. So now we need to understand what is matrix A, which is C hat, B hat, C hat, and in particular we need to understand how the spectral properties of A can be derived from the spectral properties of C and B. Yeah. So what we need is to prove the following. We need to prove that on the subspace orthogonal to all ones, like application of A doesn't doesn't make the norm of the vectors too large. So in particular, it suffices to prove the following inequality, that if I take any vector that is orthogonal to all ones, yes, and that is obviously non-zero, then if I take the scalar product of AX with X itself and divide it by the norm of X for normalization, then this should be bounded by this value. Because the maximum of this animal here is exactly the maximum of the absolute value of lambda 2 and of lambda n. This is something that we have already seen during the previous lecture. Yeah. So in order to prove that the maximum of these two eigenvalues up to absolute value is at most this number, yes, it suffices to prove that for every x that is orthogonal to all ones, we have the inequality on the right hand side. Any questions so far? Because now we are going to get into calculations. They will be actually conceptually non-trivial, but maybe there is a question about the plan. Okay, so if no question, then let me proceed. So now we need to understand this vector x that we have, and actually we need to understand what is this animal, ax cross product x. Yeah. So we will be again dividing things into parallel part and orthogonal part, but we need to be careful about this. So first of all, for every vertex v of the graph G, yes, we have this cloud corresponding to the vertex v, cloud of v. Yeah, so this is this fiber v product v of h. Right. So then I can define the indicator vector all ones on v, which is the indicator vector of this cloud. Yes. So this vector looks like all zeros, apart from I put ones exactly at the vertices of the block of v. So this means that the vertices of the form v times whatever from the graph v of h. Yeah. So this is the vector all ones on v. Yeah. And then for my favorite vector x that I'm working with, I can look at its projection onto the vector 1 on v, which is essentially zeroing all the other coordinates. Yeah, so xv is a vector that where I take x and I retain only the block corresponding to the cloud of v. All the other coordinates are being zeroed. Yeah. So then, in order to get x again, I can just sum up all these vertices like that. Yeah, because then just all the blocks are being filled with appropriate values. Yeah. So the idea is that we will be working on each of those vertices vectors xv sort of separately, and then we will combine our understanding. So now we do the usual trick in all the spectral graph theory. Namely, we'll take this vector xv and we'll decompose it into the parallel part and the orthogonal part, but in the subspace corresponding to the block of v. Yeah. So in other words, I take xv parallel to be the projection of xv onto the direction of all ones on v. Yeah. So again, this formula is the formula for the projection on the direction of one on v, and the orthogonal part is the remaining part. So this is xv minus the parallel part, and as usual in this business, this is an orthogonal decomposition. So the orthogonal part and the parallel part are orthogonal to each other. Right. So you can think about this as that this is a average behavior on the cloud of V, and this is the noise behavior on the cloud of V. Yes. So the parallel part sort of tells you the average of what is happening on the entries corresponding to the cloud of V, and the orthogonal part is just the fluctuation. Yes. And as usual in here, the average behavior is parallel to all ones, so it will behave in this regular according to the main eigenvalue, while the orthogonal part is orthogonal to all ones on V, and we will be able to understand it using a better understanding of the spectral properties on the subspace orthogonal to all ones. Yeah. So now we define the aggregate parallel part being just the sum of the parallel parts. So this is a vector that is constant on each cloud, but maybe not non-constant on different clouds, because X can have different averages on every cloud separately, while the orthogonal part is simply the sum of the orthogonal part. So the orthogonal part is sum of those noises. Yeah, so then clearly you see that that the original vector X is just the sum of this parallel part and the orthogonal part. Good. So let's make some observations about all these definitions. So first of all, let me look at. First of all, I remember that that X, yes, this vector I'm working with, this was taken from the subspace orthogonal to all ones. Yes, so the scalar product of X and all ones on the whole graph is equal to 0. But now if I take the noise part, the X orthogonal part, and I take the cross product with all ones, yes, this is the same as if I added those cross products on separate clouds. Yes, but if I take the orthogonal part XV orthogonal and I take a cross product with all ones, well, on the coordinates that are not in the cloud of V, yes, I multiply with zeros anyway, right? So this is the same as if I took the cross product with 1 and V here. Yeah? But recall that now this XV orthogonal was chosen so that it is orthogonal to 1 on V, yeah, because this was the orthogonal part. Yeah? So this is equal to 0 always. So this means that the X orthogonal part, yes, is orthogonal to the vector of all ones. Yeah, but now let me recall that X parallel is equal to X minus X orthogonal. So if X was orthogonal to all ones and X orthogonal is orthogonal to all ones, then actually X parallel is also orthogonal to all ones. And this is not a surprise in some sense, yeah, because if you have a vector that sums up to 0, and then this vector is being chopped into different pieces, and you average every piece, yes, then the vector of the averages also sum up to 0. Yeah. And this is a formal calculation of this vector. Good. So now we have this this vector, this decomposition of X into the parallel part and the orthogonal part, and we understand that this whole situation happens in the subspace orthogonal to all ones on the whole graph. Okay, so now we need to analyze what is this animal. Yeah, what is the cross product of AX with itself and the absolute value of this. Yeah, because this is necessary for getting a bound on the spectral gap of the operator A. Good. So recall that this is the same as as C hat B hat C hat, because this was equal to A, yes, times X, yes, cross product X. Yeah. So when we are doing this, we will in a moment apply this decomposition into orthogonal part and parallel part. But let's make 2 observations before we do it. First of all, if I apply my matrix C hat on X parallel, recall that X parallel is constant on every cloud. It is on every cloud it is parallel to all ones on this cloud. Yeah. So then, since C hat acts on every cloud separately, yes, and the X parallel vector has all ones on this part, is parallel to all ones on this part, then this means that on every part separately, yes, I have an application of on an eigenvector with eigenvalue d. Yeah. So this means that if I apply C hat on X parallel, I multiply X parallel simply by d, because it is multiplied on every cloud separately. Yeah. So we have this property. Second property is that we need to recall that B hat is a permutation matrix. Yes. So this means that B hat acts on any vertex on any vector by just permuting the coordinates. So this in particular means that the second norm, I always will use second norm here, of any vector is not changed by application of B hat. Yeah. So these are the 2 basic properties that we will use during the calculations. Okay, so let's go into this. We would like now to bound AX cross product X up to absolute value. And this is the same by the definition of A, by our algebraic understanding of A as this product. Yeah. So C hat, B hat, C hat, X cross product X. And because all these matrices that we are working with are symmetric, I can move C hat to the other side of the cross product. Yeah, so I can now have a cross product of B hat, C hat, and applied on X, and C hat applied on X. Good. Okay, so now we need to recall that X is equal to X parallel plus X orthogonal. So we can now write that this cross product is the sum of those 4 cross products. Yes, and because I'm working now here with bounding the absolute value, I put an inequality here because some of them might be positive, some of them might be negative. Yeah, but definitely I have inequality in this direction. Yeah, so I just open the brackets and I put all those 4 terms. Okay, so let's simplify it a little bit. Unfortunately, nothing will cancel explicitly here, but at least I see here those C hat applied to X parallel, C hat applied to X parallel, again here and again here. Yeah, and we already understood that C hat acts on the parallel part by just multiplying by D. Yeah, so I can now replace all of this by D times the parallel part, and move this D square in front here, D in front here, and D in front here. Yeah, here I also made a little bit of a change because, well, this is, by this logic, this is equal to the B hat, C hat, X perpendicular multiplied by X parallel. But now, again, using the symmetricity of the matrices, I can move B hat to the other side of the scalar product. So I've got this, and actually, not surprisingly, this element and this element are actually now exactly the same. So I can rewrite it as 2 times this thing. So now I can just apply Cauchy-Schwarz to bound all these remaining terms, yes, by the multiplications of their norms, of the norms of the factors in the scalar in the cross product. Yes, and this is the usual trick because essentially these are like noise. These are noise summands. Yes, corresponding to something involving the noise part x perpendicular. Yes, so here we just brute force bound this by the Cauchy-Schwarz. However, we leave the main part, this sort of the average behavior part intact so far. Yeah. So now we are using the fact that B does not change the norm of any vector. Yes. So then this is just the norm of x parallel, and this is just the norm of C hat x orthogonal. Yeah, so I rewrote it like that. Yep. So far we just did some calculations, and as usual we decomposed into the noise part or the error part and the average part in a sense. Good. So let's look at the noise part first, because it will be easier. Yeah. So again, if you have if you think about this matrix C, yes, we know that C, like this graph H, whose matrix adjacent matrix is C, is an d beta expander. Yes. So this means that if I take any vector that is orthogonal to all ones, this is a d dimension all ones. Sorry, like that. Then if I take the norm of the if I apply C and take the norm, then the norm cannot increase by more than factor b times d. So this means that if now again my my matrix C hat acts on every cloud separately, yes, independently, and the vector x perpendicular on every cloud separately is orthogonal to all ones on this cloud, yes, then this will be aggregated in the same way. The norm of this vector here after application of C hat cannot be larger than the original norm multiplied by more than beta d. Yeah, the largest possible second eigenvalue of the matrix C. Good. So this means that we can now transfer the understanding about the spectral properties of C to the spectral properties of C hat, yeah, and have a bound on this animal C hat applied to x perpendicular. So now I can rewrite this amazing formula as follows, that the stuff I wanted to upper bound in the first place is upper bounded now by the average part I keep intact so far, and now the C hat applied to x perpendicular I just upper bound by 2 beta d, yes, times the norm of x perpendicular, and same here. Yeah. So this norm of C hat x perpendicular square is upper bound by beta squared t square times the square of the norm of x perpendicular. Good. So now I can upper bound it like that. Again, just to get rid of all this x perpendicular, x parallel, because I know that x perpendicular is orthogonal to x parallel. This is easy to see. Then I know that what? If I take 2 times the norm of x perpendicular times the norm of x parallel times the norm of x perpendicular, this is upper bounded by the arithmetic geometric mean by the sum of squares, which by Pythagoras theorem is just the square of the norm of x. Yeah. So 2 times this is upper bounded by just the norm of x squared. Yeah. So this justifies upper bounding of this by this. Yes. While, well, here I just replaced the norm of x perpendicular by a possibly larger just norm of x squared. Good. So far we managed to really upper bound the noise part of the estimation, and we already see what we want to see at the end. Yes, this beta d squared and beta squared d squared. These are exactly the summands that should appear at the end in the final estimation. Good. Any questions at this point? Good. So let me now continue to the last part, which will involve a little bit of combinatorics, but not too much, namely understanding what is this average part, what is the remaining part that we did not estimate so far. So b hat applied on x parallel, cross product x parallel. So recall what was x parallel. Yeah, so x parallel was the sum of some vectors. The x parallel was the sum of xv's parallel. Yeah, and every xv parallel was defined as the vector of all ones on this cloud, on the cloud of v, times some coefficient gamma v, which was actually defined like that. Yeah. So then you can think about x parallel as simply the sum over v of 1 on v, yeah, on the cloud of v, times this coefficient, which corresponds to the average on this cloud. Yeah. So let gamma be the vector of all this gamma v. Yeah. So this is the vector from R to the n. Yeah, so this is a vector that lives in the space that corresponds to the graph G, not the graph G cross product, zigzag product H. Yeah. So what do we know? We know that that x parallel is perpendicular to all ones on the whole graph. Yeah. So now I rewrite it like that. Yes, as a sum over gamma v times 1 of v cross product 1 still. Yes. So now I have it, I can put gamma v in front of everything and see that this animal, the indicator vector on the cloud of v cross product all ones, this is just equal to d, because this just counts how many vertices there are in the cloud of v. Yeah. So then I see that 0 is equal to d times the sum of all the gammas. And once you think about it, nothing happened here. Yeah, it's just saying that the sum of average behaviors on the clouds is equal to 0, which we already observed before. So now if I rewrite this in the space corresponding to the graph G, I see that the vector of gammas is orthogonal to all ones in this space. Yeah, I cheated it here a little bit, because in this estimation, this is a vector of all ones on the space corresponding to G zigzag H. So this is a vector of all ones of dimension d times n. Yes, and this is a vector of all ones corresponding to the space of G, which is the vector of all ones of dimension n. Yeah. Okay, so we know that the vector of gammas is orthogonal to 0. It's orthogonal to all ones. Yeah. Okay, so now what is this animal? B hat applied to x parallel multiplication x parallel. Essentially, what is going on is that, well, here I have one cloud, say of vertex v. Here I've got another cloud of u. And now what this cross product says is that, well, on the left-hand side, I have this vertex, and it has value gamma v here. And then what we are doing is, if we apply b hat, it sends this value gamma v to its neighbor, say in the cloud of u, and then I take a cross product. Yes, so I make a product of this gamma v being sent from v and the value gamma u that was here. Yes, you can also view it as using the adjacency matrix. But all in all, this product is nothing else than the sum over all the edges of G of just the product of gamma U and gamma V. So here you need to be a little bit careful about what does it mean, product over all the edges of G. Actually, for every edge there a term will appear here twice. Once for V sending its charge to U, and once for U sending its gamma U to V. Yes, but it will appear only once for the loops. So for this is the sum over all sort of directed edges. Okay, but this is nothing else than the same process of sending the gammas to the neighbors in the graph G. Yeah, it's just that it is now distributed among the different endpoints corresponding to one vertex V from G. Yeah? So this is the same as the cross product of B gamma times gamma. So this is a cross product in R2D. Yeah? Okay, so all in all, this this term that we ended up with, yes, is the same as simply B gamma cross product gamma. Yeah? So now what we know is that gamma is orthogonal to all ones. Yeah, this is this equality here. So I can use now the spectral properties of the graph G in question. Yes, to say that this is upper bound by alpha times D times the norm of gamma. Yeah, this is just the spectral the assumption about the spectrum of G. So now, what is the relation of the square of the norm of gamma with respect to the square of the norm of X parallel? Well, in X parallel, I have simply every component of gamma, every entry of gamma repeated D times, right? So the square of the norm of X parallel is simply D times the square of the norm of gamma. Yeah. So I've got this equality here, D cancels out, and I've got alpha times the norm of X parallel square. Yeah. So just to put all of this together, we want to upper bound this animal, AX cross product X, up to absolute value. And this we divided into the noise part, which we bounded using the assumption about the spectrum of H, and the average part, which we bounded using the assumption on the spectrum of G. Yeah. So now this the norm of the X parallel part is upper bound by the norm of X square. Yes, and I have a bound like that out of it, and this is exactly what I want, because D square is the largest eigenvalue of G zigzag H. Yeah, so the regularity of G zigzag H, and here I've got this this term in front, which I promised at the beginning. Good. Sorry for being slightly late with the proof. However, I wanted to just finish those calculations. Are there any questions regarding this? Okay, if not, then this finishes the proof and the lecture for today. So we have constructed deterministically large expanders, arbitrary large expanders. During the next and last lecture of this course, we will use this knowledge for a very concrete application in complexity theory. Namely, we will prove that undirected reachability, so reachability in undirected graphs, can be solved in deterministic logarithmic space using expandarization, and in particular this zigzag construction. So this will happen next week. However, in 25 minutes, we meet for the next tutorial session on expanders. Good. So if there are no more questions at this point, thank you very much for this lecture.